Hello everyone, my name is Pepe and I'm going to introduce to you our network CGAPoseNet+GCAN that we devised to solve the problem of camera pose regression. So let's begin. By camera pose regression, we refer to the prediction of a camera pose P associated to a given frame of a video that is capturing a real-world scene. So you can imagine to be in front of King's College Chapel with your smartphone and you're moving around trying to capture a video of the scene. What you can do later is to label each frame of the video with the pose of the camera at the moment in which the frame was captured. So a camera pose P is composed of a rotational part R and a translational part T. Now, much of the effort in the literature has been focused on trying to weight these two components, R and T, because they're two very different mathematical objects. Now, this resulted in some of the most accurate pipelines, but also in a very engineering intense approaches that are not very intuitive in terms of the processing that is being done in order to obtain a good prediction. So the goal of our work here is trying to simplify the camera pose regression problem as much as possible through a pipeline that respects the geometry of the scene and in a way understands the geometrical nature of the problem. Now, there's two key elements in our approach, and the first one is the way in which we represented poses. Now, we wish to work in a different mathematical space, in a different framework, in a way that we can overcome the duality between rotations and translations. Specifically, we work in the 1D up conformal geometric algebra, 1D up CGA in short, which we indicate as G400. Now, this simply means that we're working in a 4-dimensional space that is spanned by 4 basis vectors, orthonormal, E1, E2, E3, E4, that all square 2 plus 1. Now, this is the starting point to construct two objects to represent rotations and translations. We rotate objects in 1D up CGA with rotors A, which have a scalar and a vector part. Rotors are identical to rotors in 3D geometric algebra, and they're actually isomorphic to quaternions. The second object we want to build is capital T, which again can be easily constructed from a simple displacement vector T1, T2, T3. So as you can see, it's very easy to move from standard way of representing poses into rotational and translational components in 1D up CGA. Now, a key factor about the 1D up CGA is that we can transform objects through simple sandwich products. This is a key property of geometric algebra. So, starting from a generic object X, we can rotate X and translate it by two consecutive sandwich products as follows. Now, as you can see, a new quantity appears, M, which is a geometric product of T and R, which we introduced before. Now, we call M a motor, and is characterized by 8 real coefficients, which multiply the elements of the even grade in the algebra. So M will have 1 scalar component, 6 bivector components, and 1 quadrivector component. Now, so far so good. We found a way to represent poses with a single object, the motor, which does not need a weighting between the rotational and translational part. But is this enough? Well, not really. This approach alone is not enough to obtain very accurate prediction of camera poses. So what we want to do is something more. We want to build a network that doesn't just predict motor coefficients, but predicts motors themselves, that understands what motors are and work in the same mathematical space as motors. Now, this is a key difference also compared to most of the previous literature, because predicting the coefficients of an object is something conceptually quite different from predicting an object itself. So this is the pipeline that we employed. We call it CGAPoseNet+GCAN because it is composed of two parts. CGAPoseNet is the first part because it takes inputs from our video, it takes frames as input, And then a backbone, the same PoseNet backbone, is used to predict motor coefficient proposals. So a set of 256 coefficients of a motor, hence the CGA in the name. The second part is the Geometric Clifford Algebra Network, which takes these coefficients to build actual motors which are fed in input to the network. The Geometric Clifford Algebra Network is composed of 3 geometric sandwich product layers that downsample the initial proposals into fewer and fewer poses until reaching the last one, which is the prediction on which the loss function is measured. Now, a key element of the GCAN is that the layers in this network implement sandwich products. This means that weights and biases, W and B, are also motors. So the output of the layers will also be motors, and the action of the layer on the input can be interpreted as actual geometrical transformations. Now, results are summarized as follows in the table here. You see plotted the translational error in meters and the rotational error in degrees over the test set for 13 different datasets spanning both indoor and outdoor scenes. Now, our approach has been compared with 7 other pipelines presented in literature, and we achieved some of the lowest error for most of the datasets presented. Now, this is true also for different backbones in the first part of the network, meaning that the improvement comes precisely from the fact that we have a geometry-aware approach and a network that understands what motors are and works in the same space and can perform geometric operations on them. And this really is, I think, the key aspect and the most beautiful aspect of our pipeline. The intermediate outputs of the GCAN are also poses, meaning that we can very easily visualize them and see how the network converges to an accurate prediction by downsampling the initial proposals and by seeing how they move around in the space in order to converge, to physically converge to the right pose. So, summarizing, what we did with our work is to obtain a state-of-the-art accuracy in camera pose estimation. And this has been done with a learning strategy, which is very simple and very intuitive because we just have to predict a single object now. Not just a simple strategy, but also very intuitive in the sense that we can see and interpret intermediate outputs. This has been done with a significant improvement compared to vanilla CGAPoseNet, not only in terms of lower rotation and translational error, but also with 4 million fewer parameters, as well as with an improvement over the best performing PoseNet strategy, reducing the rotational error by 33% and the translational error by 20%. Lastly, this is likely the very first use of Clifford algebra networks in a computer vision task, and we have reason to believe these kind of networks are going to be used more and more in these for these problems, since a lot of data in computer vision, of course, have an intrinsically geometric nature associated to it. So this will be everything for our work. So thank you so much for the attention, and I hope you enjoyed it, and I hope to see many of you in person in January at WACV. So thank you so much for the attention, and see you soon.